Okay, now we start to learn Chapter 4, Linear Transformation. Section 1, Definition and Examples. Part 1, Definition and Simple Examples. First is definition. A mapping L from a vector space V into a vector space W is said to be a linear transformation if we have this relation 1, L function on alpha x plus beta y equals alpha times L function on x plus beta times L function on y. So we need this one for all x, y belong to V and for all scalars alpha and beta. Okay, and we can also write equivalently as two relations. L function on x plus y equals Lx plus Ly, and also L function on alpha x equals alpha times alpha x. Thus, L is a linear operator if and only if L satisfies 2 or 3. So that means in order to check whether mapping L is a linear transformation or not, you can check only the formula 1, or you can check both 2 and 3. So 2 and 3 is equivalent to 1. Okay. Now we see simple examples. First, we see linear operators on R2, two-dimensional real vector space. Okay, let L be the operator defined by L of x equals 3 times x. So ask you to prove that L is a linear operator. In order to check L is a linear operator or not, we calculate about L function on alpha x and L function on x plus y, where x and y are arbitrary vectors in R2 and alpha is an arbitrary real number. Okay, so L function on alpha x equals at this definition for this linear operator, for this operator, it's 3 times alpha times x, and we can put alpha out, which equals alpha times 3x, and we know that 3 times x is just L function on x, so we have L function on alpha x equals alpha times Lx. And then for this addition x plus y, we know L function on x plus y equals, at this definition for this operator, it equals 3 times x plus y. And by the distributive property, we know this one equals 3x plus 3y, where 3x is just L function on x and 3y is just L function on y. So after we show these two equations hold, then we know that L is a linear operator. And in general, for alpha greater than 0, the linear operator f of x equals alpha of x can be thought of as a stretching or a shrinking by a factor alpha. See? So if alpha greater than 1, it's a stretching. Okay? If alpha greater than 0, no more than 1, smaller than 1, it's a shrinking. Okay. We see another simple example. Let L be the operator defined in this way. L function on x equals x1 times e1. E1 is a coordinate vector, 1, 0. Okay, this is a two-dimensional vector. Prove that L is a linear operator. So we can see from this figure what is the operator means. Okay, so here is x, and if I do this operator function on x, we will find here this vector, okay, x1 times e1. So this vector, in fact, should be the projection vector along the x1 axis for this vector x. Okay, The proof should be very easy, right? You can just check L function on alpha times x for arbitrary real number alpha equals alpha x1 times e1, right? So if equals alpha times Lx, and you then check L function on x plus y should equals x1 plus y1 times e1 equals x1 times e1 plus y1 times e1. So equals L of x plus L of y. Now we consider this simple example. Let L be the operator defined in this way. So L of x equals x1 minus x2. So we keep the first coordinate unchanged. But for the second coordinate, after you do this operator on x, we get the opposite value for x2. So from the figure, it's just like this. When x is here, you will find L of x here. So L of x should be the reflecting, right? Reflecting using this x1 axis. Okay, so this linear operator L has the effect of reflecting vectors about x1 axis. Okay, another example. Example 4, let L be the operator defined in this way. So L of x equals minus x2 x1. So after you do this operator, the first component is minus times the second component for the original vector x. And its second component comes from the first coordinate of the original vector x. So from this figure, we can first see what is L. When the original vector x is here, because your new vector after function on x using this L, you will get this one. So minus x2 x1. So these two vectors, like they are perpendicular, they have the angle 90 degrees. Okay, so this linear operator L has the effect of rotating each vector in R2 by 90 degrees in the counterclockwise direction. So this is also a linear operator. You can check. You have L alpha x equals alpha times Lx, and you can check also Lx plus y equals Lx plus Ly. Now we see another example, example 5. Let n be the operator defined in this way. So n function on vector x equals x1 power 2 plus x2 power 2, then do the power 1 over 2. For this operator, is it a linear transformation? The answer is not, because if you compute m alpha x, so m alpha x equals, you can put alpha in alpha x1 power 2 plus alpha x2 power 2, then do the 1 over 2 power 1 over 2. So when you get this scalar out, should be alpha absolute value times mx. So when alpha is smaller than 0, you have this inequality. So m alpha x does not equal to alpha times mx. Hence, this mapping, this operator is not a linear operator. Okay. We see this example. Let L be the operator defined in this way. L function on x equals x1 plus x2. You can check directly that L function on alpha x plus beta y just equals alpha times L of x plus beta times L of y for arbitrary scalars alpha and beta, for arbitrary vectors x and y in R2. So this L is a linear transformation. And now we consider other examples which are linear transformation from R2 to R3. Okay, so given you x in R2, and we define this operator, L of x equals x2, x1, x1 plus x2. So the first component of Lx comes from the second component of the original two-dimensional vector x. And the second component of Lx comes from the first component of the original vector x. And the third component of this L of x comes from the summation of the two entries, two components of the original vector x. And it is easy to check that L function on alpha x equals alpha times L of x. And you can also check that L function on x plus y equals L of x plus L of y. So this is really a linear transformation. And for this example, if we define a matrix A in this way, so A equals the first row 0, 1, second row 1, 0, third row 1, 1, we can show that so L of x in fact can be written as A times x. So LAX equals AX. So LA is a linear operator where L of x is just x2, x1, x1 plus x2 defined here, and you can find it just coincides to this matrix A. This matrix A times x for each x in R2. Okay, and now we consider linear transformation from Rn to Rm. We see this example. Let L be the operator defined in this way. LAX equals A times x. So original vector is x. After you do this operator, do this function, you will find A times x. Okay, so for each n by n matrix A and each x in Rn, the operator LA is a linear transformation. Since L function on alpha x plus beta y equals A times this whole vector alpha x plus beta y, and by the matrix multiplication, you immediately know that it equals alpha times ax plus beta times ay equals alpha times lx plus beta times ly. So this operator is a linear transformation. Okay, so we can think of each n by n matrix A as defining a linear transformation from Rn to Rm. And we have these properties for linear transformation from V to W from two different vector spaces. Okay, if L is a linear transformation mapping vector space V into a vector space W, then we know that L function on 0V equals 0W. So this means the 0 vectors map to 0 vectors by linear transformation. And secondly, we know that L function on A1V1 plus A2V2 plus TL plus ANVN equals A1 times LV1 plus A2 times LV2 plus TL plus AN times LVN. So you can have this equation. Okay. And thirdly, we know also that L minus V equals minus LV for all V belong to this vector space V. We see the proof very easily. The first one can follow from LAV equals A times LV by the definition with and we choose special A equals 0. So if A equals 0, you know that 0 times V is a 0 vector in the space vector space V, and here 0 times LV should be the 0 vector in the W space. So immediately you have the first statement holds. Okay, and the second one, you can do this as exercise because it's very easy to show using the mathematical induction. Okay, and thirdly, for this one, because 0W equals L0V, this comes from the first statement. This one equals L, because 0v equals v plus minus v, using the axioms for vector space. So this one equals LV plus L minus v. This one comes from the definition for linear transformation. And then you will know L minus v equals minus LV. Okay. Now we see another example for linear transformation from V to W from general vector spaces. If V is any vector space, the identity operator I is defined by IV equals V itself for all V in this vector space. Clearly, I is a linear transformation that maps V into itself. And of course, I function on alpha V1 plus beta V2 equals alpha times V1 plus beta times V2 equals alpha times IV1 plus beta times IV2. The other example is example 9. Let L be the mapping from CAB to R1 defined in this way. So L of F equals this integral. Prove that L is a linear transformation. So in order to show that L is a linear transformation, you should check whether L alpha F equals alpha LF, and whether L function on F plus G equals L function on F plus L function on G. Using the properties for this integral, you can show this easily. Okay. Another example is about differential operator. So let D be the mapping from C1AB to CAB defined by D function on F equals the first order derivative of F. Prove that D is a linear transformation. So it is easy to find that D function on F plus G equals F plus G derivative, which equals F derivative plus G derivative. So equals D function on F plus D function on G. And also, it is easy to show that D function on alpha F equals alpha F derivative equals alpha times F derivative equals alpha times DF. So D is a linear transformation.